All right, so with that, I want to introduce our lightning talk speakers. First up is Cesar Meza. He's a senior and he's an incoming graduate student in our department. And then after Cesar, we'll have Anna Wadhwa and Annika Thomas, graduate students. Okay, let's go.
I'm assuming this is the clicker right here.
Yep.
Perfect. Excellent. Well, we're running short on time, so I'll go ahead and keep this brief. Thank you kindly for joining me. My name is Cesar Meza, and I'm here with the Human Systems Laboratory, and I'll present some of my work, which I've been doing for a year and a half, on cyclical electrostatic regolith beneficiation. So as we start to imagine the future of a prolonged human presence on the moon, there are a lot of resources and requisitions that our missions will require, namely a habitat infrastructure, photovoltaics to essentially power all of our operations, consumables such as propellant, perhaps even water and oxygen that we need to maintain human operations on the moon. And all of this renders a very important question. Should we make this on site? And this gets to the heart of in situ resource utilization as a discipline. My research focuses within this discipline, particularly in that of lunar metal extraction. Lunar regolith is the mixture of minerals and rocks that's prevalently found on the surface of the moon. And there's one mineral in particular that's both energetically favorable and most abundant, and we can separate it into oxygen and iron using a process known as molten regolith electrolysis. Iron, which we can use for infrastructure and construction, and oxygen, which we can use for consumables such as water, propellant, and life support. So the production pipeline for any metal that's extracted on the moon will look something like this, where we have extraction and excavation of lunar regolith, then beneficiation, or the enrichment of minerals of interest in that sample, and then finally running it through a furnace or a molten regolith electrolysis generator. My research focuses exclusively on beneficiation, namely electrostatic beneficiation. The concept is quite simple, even though it is quite a mouthful. Essentially, what you're doing is you're running samples of lunar regolith through a very high energy electric field, and because the different minerals within lunar regolith can accumulate different charges based on their composition, you can actually stratify a sample of lunar regolith into different piles of minerals. Where does the cyclical come in? I'm glad you asked. Well, if we take the pile that has the largest concentration, percent weight, of ilmenite, and we run it through again and again and again to remove as much waste as possible, we can start to gain insight into two critical questions. Namely, what's the highest percent weight of ilmenite that we can extract, and how does this compare to the earth-based processes that we currently employ in other industries? And finally, is it even worth it? Should we be funding this research? Should we have a technology demonstration of this capability, and can it potentially help us establish a prolonged presence on the moon? So I've been working on this project for about a year and a half, and the setup, although it has changed over time, remains relatively the same. Primarily, it has a funnel feeder system, which goes through a turbocharger. It's kind of like when you get a balloon and you rub it on your head and you induce a separation of charge. Yeah, we're doing that to the regolith so that when it goes through a 20 kilovolt potential difference across these two copper plates, it stratifies into different piles of minerals, and I can collect them and run some SEM on them to indicate whether or not we've actually successfully enriched the concentration of ilmenite within a given sample of regolith. I would show you a video, but it's not very interesting, namely because my camera quality is absolutely terrible and can't capture the finite size of lunar regolith as it falls through these two copper plates. But you can see that when you apply an electric field, there is a clear difference in the distribution of the particles as they pass through the system. And what I'm about to show you is preliminary, so please don't take this as ground truth. This is not really publishable material, but it does have it presents us a useful starting point for whether or not this technology is actually reasonable and worth investing in. Well, I've been able to isolate on average about 2 milligrams of ilmenite from 10 grams of regolith after 3 passes. And granted, this is 10 times less efficient than Earth-based flotation separation methods for ilmenite and other iron-rich minerals in Earth excavation, but it serves as a useful starting point to see that not only can we separate lunar regolith using a very strong electric field, but we can optimize this process by doing it multiple times. And this is the work that I've been working on for the past couple of years. I'm excited to continue working on it, and I certainly believe that by focusing on all of these different parts of the lunar metal production pipeline, we can best support the future of what we hope to have, a prolonged human presence on the moon. If you have any questions, comments, concerns, I will be here for a while, and also I invite you to please connect with me into some capacity. I'm happy to talk about my research, and that is 5 minutes. Thank you kindly for your time.
It's already up. Hi, everyone. My name is Anna. I am an MD PhD student with Harvard and MIT AeroAstro, and today I want to talk to you about artificial gravity. Now, artificial gravity is not a new concept by any means. Whether we go back to the 60s with one of the best sci-fi movies of all time, 2001: A Space Odyssey, or to companies today like VAST that are trying to build the space stations of the future, Haven 1, Haven 2, equipped with artificial gravity. But where is the data on this? Where is the data on whether or not artificial gravity is good for us, on whether or not, how does it impact our physiology? That's what we're trying to answer today. So that was the goal of the MHU-8 mission, which was the first ever partnership between NASA and JAXA, the Japan Aerospace Exploration Agency. And with MHU-8, we wanted to understand how artificial gravity, different levels or different amounts of it, actually impacts our physiology. I'm going to be speaking about the bones specifically today because we know bone loss is so critical. It's such a critical problem for astronaut health. They're doing exercise for hours a day on the International Space Station, but even that's enough. So the question then becomes, can artificial gravity bridge that gap? Is it going to be a viable countermeasure for the future? Let's find out. We study this using something called the Multiple Artificial Gravity Research System, or MARS, developed by JAXA, and it's the centrifuge-equipped cage assembly for mice. And once it's up in space, depending on the speed that it rotates at, the mice will experience different levels of artificial gravity. So for example, in the middle, you can see one mouse, our moustronaut, if you will, experiencing microgravity. On the other hand, on the right, we have a mouse in artificial gravity, specifically 1G, and he's scampering about just fine. We wanted to understand how different levels of partial artificial gravity specifically will be impacting the bone loss. And this is because if we want to go back to the moon, if we want to go to Mars, we have to understand how these partial gravity environments are going to affect our physiology. The question is not just, can we do it? But can we do it safely? Can we do it in a way that will optimize astronauts' health and performance during long-duration missions like this? And so, with MHU-8, we sent mice to the International Space Station for 30 days, where they either experienced 0G, like the little moustronaut in the middle, 1/3 G, 2/3 G, 1G, or ground-based controls that we had here on Earth. Looking at their bone structure and their bone strength, in the middle is a graph of trabecular bone structure. On the right is a graph of their predicted strength using finite element analysis. And what we can see is kind of an interesting pattern. So going from left to right, we have 0G, 1/3 G, 2/3 G, 1G, and then our ground-based controls. And what's first noticeable that I want to point out is that 1G was not significantly different from ground-based controls, which is fantastic. But another thing that I think is a little bit more subtle is that this isn't a monotonic increasing pattern. That is, it's not exactly a dose-associated relationship, which is interesting. And then going one level deeper, looking at their gene expression, this is a heat map analysis, which basically looks at all of these genes that have changed their expression patterns between the different groups. So on the leftmost, we have our ground-based controls. And then again, progressing, we have 0G, 1/3 G, 2/3 G, and 1G all the way on the right. And the colors indicate how similar or dissimilar the gene expression patterns are. So for example, comparing the first two groups, ground-based controls and 0G, we see that the colors or the gene expression patterns are very different from one another. As we move higher and higher in our artificial gravity level, we can see that the colors and the gene expression patterns start to resemble ground-based controls, and that's fantastic. What's another thing that's interesting is that this appears to be more of a dose-associated relationship, which is different from what we saw with bone structure and strength. What does all that mean? Basically, the main conclusions are that 1, we can see that artificial gravity does mitigate changes in bone health during spaceflight. Notably, Martian gravity, approximately 1/3 G, was not sufficient, but we did see near complete preservation of bone health at 1G. This has implications, in my opinion, for how companies like VAST should be trying to target 1G levels of artificial gravity in the spacecrafts that they're developing. Right now, I think they're targeting lunar gravity, as far as I know. The second point is that we did not see a dose-associated relationship for bone structure and strength, and only saw that for gene expression. Why that's the case? $1,000,000 question for us. We think it's probably some combination of low sample size, as does plague every spaceflight mission, probably also a shorter experimental duration, about 30 days, might not be enough for gene expression patterns to translate into bone structure and strength. We're still working on that, but this is what I have for you so far. So going back to that original question of artificial gravity being science fiction versus science fact, where does it stand right now? Probably somewhere in the middle. It's maybe a little bit of both. I think it's really going to hinge on what level of artificial gravity we can even achieve with the spacecraft that will determine whether or not this is actually a viable countermeasure. I'm excited to see what the future holds. Thank you.
Hello, my name is Annika Thomas. I'm a PhD candidate here at MIT, and in my research, I teach robots how to see. More specifically, I teach robots how to understand and navigate complex unstructured environments like the lunar surface. NASA is planning to send the ISRU pilot excavator, or IPEX, to the moon in the next couple years. But the current concept of operations is limited to a pretty small scale space. And that's because mapping visually on the moon is pretty difficult. We have really harsh lighting conditions, we have unknown obstacles, unknown terrain, we have to perform that path planning in real time and kind of handle all of these obstacles with these different types of concepts of operations that we can't necessarily plan for every single case ahead of time. So I've been working with a team of undergraduate and graduate students over the last year to develop an autonomy system that's capable of scaling this autonomous operation beyond that small scale environment up into larger scale environments. So we've developed a full autonomy system consistent with navigation, perception, localization, and power management paradigms. Our localization uses visual inertial odometry. So we're basically extracting meaningful features from the environment and tracking them from frame to frame in order to get an estimate of where our rover is in the frame. We're using stereo vision, which is kind of the same type of vision that you and I use for depth perception with our two eyes. Our perception platform uses object detection and terrain mapping. We take images that look like this from the rover, as well as the depth information that we get from those two stereo cameras. And then we perform open set segmentation. We're not relying on doing any kind of class-based modeling or training because we don't necessarily have training data for the moon. So we're able to leverage foundation models that can perform this class-agnostic instance segmentation in order to extract objects from the environment. Once we have these different components, we're extracting features from the environment as well as the location of objects. We can create these robust maps that basically incorporate elevation information as well as the location of rocks so that we can avoid craters, those difficult parts of the terrain that we want to not necessarily drive into. Our power management is tightly coupled with the navigation platform. So basically, we are intelligently using the resources on board in order to perform this mapping, but also we have to figure out very robust ways in order to drive the rover right up next to the lander in order to perform this charging maneuver. I got a lot of questions today about what these QR codes are. These are called April tags, and they basically allow us to get an estimate of where our rover is in the frame. So we can use that once we get nice up and close and then charge our rover. And finally, bringing this all together, we have a navigation paradigm that's basically able to compute both high-level and low-level navigation throughout the lunar environment and create this navigation and autonomy stack. So we've developed this kind of robust method to create a map that has to do with the underlying structure of the environment. Things look a lot different as the sun moves around in the lunar sky, vice versa, because we have these really harsh shadows. So we want to create these maps that have to do with the underlying structure of the environment. And while I would love to get into the technical details and all the modules that make this happen, I'll save you from that for now, but we do have an exhibit outside, so please feel free to stop by if you're interested. But I will leave you with this. Autonomy is at the core of the future of space exploration. And in order for our robots to be more than a collection of sensors, of cameras, IMU, we really need to teach them how to map the environment, not only accurately, but also intelligently. Thank you so much to our team, to our advisors, George included, and thanks for listening.